This is the third web talk in the M+ Web Talk series. Web talk number 3 discusses a new type of structural equation model for longitudinal data. It does that by revisiting a well-known SEM example, the so-called Wheaton et al. Model that was published in 1977 as a chapter in the annual book Sociological Methodology. Since then, this paper has been cited numerous times. The model has been used as a classic example in many SEM courses, and it has been featured in several SEM software manuals as well. Web talk number 3 is a bit different than the two previous web talks in the M+ Web Talk series. It has a little lighter touch in that it gives a bit of history behind my participation in this paper, a paper that was conceived 46 years ago. It's quite amazing that a better fitting model has been found so many years later. Like web talk number 2, the new modeling in web talk number 3 is derived from the modeling ideas discussed in web talk number 1. The relevant modeling ideas will be reviewed here, but the web talk will also discuss the M+ scripts for both the classic and for the new model. Following APA conventions, this web talk can be referred to as shown here. On slide 2, I give the outline for the web talk, starting with the history of how this model formulation came about, and then going back into modeling ideas, which derives from multilevel factor analysis. And then we get to the new longitudinal SEM for the Wheaton et al. Data. And then ending with discussing the M+ scripts. Turning to slide 3, I will give you a bit of history behind this paper of Wheaton et al. Took place 46 years ago at the University of Wisconsin, Madison, Wisconsin, during the academic year of 1974 to 75. At that time, I was a graduate student in statistics at the University of Uppsala, Sweden, under the mentorship of Carl Jörskog and Anders Christoffersen. Back then in Sweden, there were not any SEM researchers, and mostly we got our data from the US. And I was curious about going to the US and connect with some people who had interesting data sets and problems to come up with, be inspired to come up with new statistical modeling for my dissertation. And I visited with a colleague of Carl, namely Art Goldberger, who was in the Department of Economics, which is on the right here, to the right of the bell tower. And Art Goldberger had interacted with Carl Jörskog several times in the structural equation modeling area. They had a paper together, for instance, in JASA, Journal of the American Statistical Association, on mimic modeling from an econometric and a psychometric perspective. And there was also the Department of Sociology housed in that building with Bob Hauser, for instance. And one of the first days I came into Art Goldberger's office with a beautiful view of the lake, he pulled out a note, a couple of pages that been put together by the sociologist Otis Dudley Duncan, where he had formulated a problem that he didn't solve that had to do with dichotomous dependent variables in a structural equation model. So that was fortunate. He provided the data as well, and I came up with the modeling, and that became the first paper in my dissertation and got published in JASA, my first and only JASA article. But that article didn't become very well known. Instead, another paper that was created during that time became very well known, the so-called Wheaton et al. Article. So that came from an interaction with Blair Wheaton, who was a graduate student in sociology at that time. A very hard-working guy who had data from Alvin and Summers and was struggling with structural equation modeling efforts, trying to find a reasonably well-fitting model. And I came in at the right time there to help along with the modeling and the literal runs. And out came eventually this paper. The model is like this. We have measures, anomia and powerlessness, measuring an alienation construct at 3 different time points. And we have an SES construct measured by education and a socioeconomic index created by Otis Duncan. And Blair's contribution here was to estimate the stability between, that is the regressions between these factors over time, controlling for SES, and also adding measurement error to the indicators, the outcomes here, thanks to having multiple indicators. My contribution was, I just learned about this in Uppsala, to say that, well, you really should allow for correlations between the residuals, the errors of each indicator at least adjacent time points like this for the first indicator and for the second. And that enhances the fit quite a lot, picking up a lot of influences, time-specific and item-specific influences that are omitted, that are unobserved variables, and therefore get picked up by the residual and needs correlations among the residuals. Now, it's easy to criticize this model in hindsight, and I do so in our M+ short course topic 1 video from Johns Hopkins. We have a 2009 recording, for instance, with slides 231 to 238 being the relevant ones. And the major problem here is, of course, that you only have 2 factor indicators. And that's not a desirable situation. You should try to avoid that if you can. Because what you want to do when you have a model like this, you want each part of it to be correct. And you have many parts here. You have this measurement part, this measurement part, this measurement part, this measurement part. Preferably you want to test each of those parts and combinations of the parts as well. But you can't in this case because you have only 2 indicators and you need 3 indicators for the model to be just identified. And in that case you can't reject it because it is just identified, so you really need at least 4 to be able to test it. So the fact that you can't test it means that you may introduce various kinds of misspecifications in the model that then may spread and not only affect the measurement part but also the structural part. So I discussed that in the topic 1 video. In our defense, Blair's and I, we actually started with more items to begin with, but it was hard to find a unidimensional construct for some of the items. So we boiled it down to 2, and it became an article that at least was a good example of a new kinds of structural equation model, although it's not the strongest one due to having only 2 indicators. Another critique could be that this construct is not really perhaps believable. It says that you have inside of you some sort of SES dimension, and as it increases you seek higher education and higher paying jobs. Whereas perhaps a more natural way of looking at it is that you have an education that may influence the job that you take, and that builds up your SES status. So the arrows go the other way, and instead of having what's called reflective factor indicators, you have a formative situation, which might be better. Now, putting that aside, it's still a good example of the key issue of a longitudinal SEM, 3 time point SEM. And let's see what we can do with that. Now, in the standard situation, the standard model version here, would be that you have metric invariance for the measurement part. That is time invariant factor loadings. So these factor loadings are equal across time. That's necessary, of course, to make sure to some extent that you have the same construct in the same metric. And also correlated residuals, like I mentioned, for each factor indicator and at least for adjacent time points. So that's what I would call the classic version of the Wheaton et al. Model. In our article, Blair and I went into all kinds of contortions to find a more relaxed model that fit better, but I think this is sort of a good point to stop at. Chi-square is 90 with 13 degrees of freedom, so we reject the model with the help of the p-value being 0, although this is 900 individuals here, so it's a fairly large sample, fairly strong power, ability to reject the model. The RMSEA is also not great. CFI is good, but that's a very forgiving index in many cases. Now, turning to the next slide, what if I told you that in addition to the classic model, there is a new model which has 6 fewer parameters, more degrees of freedom, that is a more restrictive model, but still a better chi-square? Well, that's the model that I stumbled upon recently, some decades later. It has a much better BIC because, lo and behold, despite the lower number of parameters, you have a higher log likelihood, and therefore you have a much better BIC, the better chi-square, actually a little p-value here at 4%, and RMSEA that goes down very nicely, and almost a unit perfect CFI. So what I want to do in this web talk is describe how this new model comes about and show you the picture of it and show you how to set it up in M+. Now we're going to try to explain how the new modeling came about that fitted the Wheaton data better. So on slide 8 we have the outline showing that we're going to draw on modeling ideas from multi-level factor analysis. On slide 9 then you have a model, a vector of observations or variables y for individual I in cluster J, decomposed into an intercept or a fixed effect and 2 random effects, that is 2 latent variables, one on between varying across the clusters J and one on within varying across individuals within cluster J. And this is the regular random effects ANOVA decompositions, these 2 parts being independent. And for each of these B and W components, we assume a factor structure with a factor loading matrix lambda and a factor vector F and the residual vector epsilon, both for between and for within. And that gives us a covariance structure for the observed y vector, which is the sum of the between and the within covariance matrices. And each covariance matrix then has a factor model structure of the standard kind, lambda, psi, lambda prime plus theta, where psi is the covariance matrix for the factors and theta is covariance matrix for the residuals. This seems to have started, this interest in multi-level factor analysis, with an article by Lee Cronbach, or a research paper rather, in 1976, where he did research on classrooms and schools, and that is clearly hierarchical data, students within classrooms and students within schools. And in 1978, or actually earlier than that, Kjell Härnqvist from Sweden came over and visited Cronbach at Stanford and got inspired, went home to Sweden and wrote this paper of primary mental abilities of collective and individual levels. Now, at that point, the estimation of the model was quite rudimentary, for instance, to get the between matrix estimated sigma b, they simply created a covariance matrix, a sample covariance matrix, that started with the means in each school, the observed means, so y bar in each school, and did a covariance matrix for that. It's not quite right, but it gets close to what you would get if you do a more efficient estimation. And then later on, Harvey Goldstein and Rod McDonald started working together on the general model for the analysis of multi-level data. They had a psychometric article, and then another McDonald and Goldstein article in British Journal of Mathematical and Statistical Psychology, focused on how you would express the likelihood for maximum likelihood estimation. And I took an interest in this when I read those articles. I was inspired by notes from Rod McDonald, quite detailed notes. So in 1989, I wrote a paper, an overview paper, part of which dealt with multi-level factor analysis estimation, because at that point there wasn't a general computer software program to actually do the analysis. And playing around with the formulas, I noticed that you could use multiple group SEM analysis using, say, Lisrel. And in the case of all clusters having the same number of individuals in them, you could actually get maximum likelihood estimates out of it. It would be a two-group analysis, one for analyzing the between-level part and one for analyzing the within-level part. And in 1991, I looked at various kinds of applications of that in analysis of class and student achievement components. And then I wrote an overview paper that dealt more specifically with how you would go about the analysis, the multi-level analysis, which steps you would take. And I focused very much on students within classrooms or schools and achievement testing. And it's clear then that there are typically fewer between-level factors FB than within-level factors FW. And the FB interpretation is quite different from the FW interpretation. So for instance, on the within level, you may measure a student's math and reading skills and come up with, say, 2 factors that are correlated. But on the school level, these measures are more influenced by general school excellence. So a single factor on between and 2 factors on within. Now, if you take a look at this factor model in more detail, we can write it assuming that we have only one factor on each level. So instead of a matrix lambda, we have a vector, and we have only one factor, single factor here. Same thing on the within level, single factor on within. So if you look at this expression, you can actually write it in a different way, in a 2-level fashion. So on level 1, you can write it as y equals an intercept nu that varies across clusters, plus the within part, factor structure on the within part. And then you can say that nu, this random intercept, has an overall mean and a variation across that mean that is the between part. Now if you insert this nu j expression into equation 1, you get the expression that we have at the top. But by writing it in this fashion, as those 2 equations, it becomes clear that we're dealing with a random intercept here. You know, whatever is random has a subscript j on the right-hand side. Lambda doesn't have that in this application, but you could. But the intercept has it. So it would correspond to item bias or differential item functioning if you talk about measurement invariance matters. So 2 key aspects. 2-level factor analysis can be viewed as a random intercept model where the intercepts have a factor structure. You don't have to have a factor structure. You can have just totally freely correlated intercepts if you want to. But very often you can reduce the dimensionality into one or a few factors. Now, because the random intercepts appear for the factor indicators in this equation, we allow for a certain form of measurement non-invariance. That is, y as a function of the factor differs for students in different schools j. So there is something about the school context that makes your achievement score, for instance, lower or higher. So the measurement model is not the same for all students in the whole sample. So that's a form of allowing for measurement non-invariance. Doesn't mean that we have to throw out items that have bias, but it just means that if we have to model it, we have to represent it. Turning then to slide 12, I repeat these two equations, the level 1 equation here and the level 2 equation, and try to show this in diagram form because it's easier to talk about general modeling and relationships between models through diagrams than formulas sometimes. So we have here on the within level, that's level 1, we have y expressed as this right-hand side. So we have the observed y's, and the random intercept is marked by a filled circle here, the intercept in the measurement equation. And then the lambda w's are loadings on these paths. And we have FW here, and the short arrows here correspond to epsilon within. And then these filled circles, marking the fact that we have a random intercept, become open circles, that is continuous latent variables on the between level, that is level 2, that is nu j is equal to nu plus lambda b fb plus epsilon b. So here we have the fb, lambda b loadings and epsilon b, and here nu1, nu2, nu3 are the three different random intercepts. And the covariance structure then on within is sigma w, that's the variances and covariances among the part of the model that is represented by these two terms, and sigma between represents the covariances among these variables, these three variables, which is represented by these two terms. On slide 13, we will be going deeper into multi-level factor analysis and take a close look at the covariance structure for students within schools. And we're going to show the data in a different fashion, showing the data for each student. This is a way of displaying the model that's often used in statistics and in econometrics. So as a simple example, we have school 1 and school 2, and we consider 3 students in school 1 and 2 students in school 2. Each student has then a data vector y that contains the 3 variables that we talked about on the previous slide. 3 variables here, 3 here, etc. down. So considering the first student here then, the covariance structure for that student is the sigma w plus sigma b that we've talked about. The sigma w coming from the within level part of the factor model, and sigma b coming from the between level part of the factor model. And every student has that diagonal element, sigma w plus sigma b, all the way down here. And that's because we assume that the students come from the same population. Now down here we have zeros because students of school 2 are uncorrelated with students in school 1. And that's because we do random sampling of the schools. So we have independent observations across schools. Now within a school, you have a covariance between each student, that is sigma b, and that is a non-zero element. And there it comes about because they share the same school. This is the same for students in the same school. So we get a sigma b contribution here in the off-diagonal. And that's what creates the intra-class correlation. It's the numerator of that intra-class correlation. So we have 3 of those sigma b's for those 3 students and 1 for these 2 students. And in statistics or econometrics, this is usually expressed with help of matrix algebra Kronecker products. Now, what does this model mean then, and how should we look at it? Well, it's interesting. We can show it in a very simple fashion in the model diagram on slide 14. So here we consider the simpler case of 2 students for each of the schools. So here is student 1 and here is student 2. So we have sigma W for each of the students, same sigma W, and we have sigma B that the students have in common. So the observations on these 3 variables and these 3 variables are correlated because they're influenced by the same school random intercepts. The random intercept for the first variable influences y11 and y21 with coefficient 1. So all of these variables correlate because they share the same school. Now, of course, we could have a more general model. You could, for instance, consider in small group research a leader and a follower and have an arrow from student 1 to student 2. That is, a correlation between the students beyond the correlation that comes from their common influence from the school random intercepts. Now, what are we looking at here then? We have quietly made a paradigm shift, because how would you analyze this? And what is the model? Well, the model is the same as what we talked about on slide 12. It's this multi-level model, just shown in a different way. And it's different because we would not analyze this by 2-level analysis. We would analyze this by single-level analysis in wide format. Wide format because we have not only 3 variables, but we actually have 6 variables. 3 for each of the students. So it's a wide format analysis that estimates the same model parameters as the 2-level model and 2-level analysis. Now, typically you would not do 2-level analysis in a wide format, certainly not with many students per school. Say that you have 10 students, then you would have 6 times 10, 60 variables to contend with. So that's not practical. And that's why you benefit from 2-level analysis. But there are cases where you have relatively few members of each cluster. So here we're talking about cross-sectional analysis, students within schools. But what about longitudinal analysis, where you also have time points, where you also have a nestedness, that is time points nested within individuals? And there you would have relatively few members per each cluster. This would be 2 time points. It wouldn't be too hard to expand this to 3 time points or 4 time points. And then you end up with a single level wide analysis of longitudinal data. And here you have the model on slide 15. Now we have t equals 2. That is time point 1, time point 2. It's the same individual at the 2 time points. And the reason the variables correlate across time is because they share the same individual random intercepts for each of the items. So that creates the correlation across time that we want. And that's been brought up. That idea has been written about by Hammacher in a 2016 multivariate behavioral research article that seems to have gotten lost in researchers' everyday analyses. She talks about modeling that comes from multi-level factor analysis, inspired by multi-level factor analysis. And she argues then that factors from cross-sectional analysis are partly determined by between and partly by within person covariance structures, citing Cattell in 1978. And that really reflects this uninterpretable blend of within and between parts of a multi-level model that Raudenbusch and Breich have talked about in their 2002 book. Now, multi-level based longitudinal factor analysis allows for these differences between person and trait. There are trait-like factor structures, FB, and within person state-like factor structure, or FW, at the different time points. And it's sufficient actually to have only 2 time points, as in the picture we drew, to determine this within person factor structure. You don't need the intensive longitudinal data to estimate a factor model for each person, the so-called n=1 analysis, or Cattell's P technique. And this relates to latent state trait work, which has a lot of articles that emanated with the latest one in the series is Chris Geiser's 2020 book on longitudinal structural equation modeling from a latent state trait perspective. So now, if you then take this longitudinal factor analysis based on multi-level thinking and have individual at the top level and time at the bottom level, we can add this path between the 2 time points, time point 1 and time point 2. So that's an autoregression for the FW factors, for the within factors. So that would correspond to a cross-sectional model that I talked about before, where students within school, 2 students within a school, influence each other. So this multi-level based longitudinal model is quite different from the usual naive longitudinal model, which uses only the bottom part here, perhaps adding some correlated residuals across time where you would need them, but not in this disciplined fashion of having one set of random intercepts that have influence on all the outcomes at both time points. Okay, turning to the outline on slide 18, we're now ready to apply our modeling ideas from multi-level factor analysis to create a new longitudinal structural equation model for the Wheaton et al. Data. To remind you, here is the traditional Wheaton et al. Model with 2 indicators, anomia and powerlessness, for each of 3 time points, influenced by an SES factor measured by 2 indicators. So let's see, what will this picture look like if we bring in the thinking from multi-level factor analysis applied to the longitudinal setting? This is what it'll look like. So on the right here, we still have the 3 time points with the 2 measures, anomia and powerlessness. On the left, now we have something new. A random intercept latent variable, A, for anomia and P for powerlessness. And they have influence on the observed indicators with coefficient 1 at all time points. They each contribute a parameter of variance, or in this case actually a residual variance, because now we can say that these intercept variables are really between person variables, what varies across individuals. And what varies across individuals is the SES as measured by education and SEI. So conceptually, we can draw a line here between the between part, between individuals, and the within part, which is variation across time. So the between individual variation is, these correspond to FB, or indicators of FB rather. The random intercepts that vary across individuals. And they are the ones that are influenced by SES, which varies across individuals, but not across time, according to the Wheaton model. It doesn't vary across time. It's one SES measure, time invariant latent covariate. So we would draw it this way, and we make a line here between the between person, the within person variation. So on the right, we have variation within person, but across time. Is the across time variation within person, free of the between level, the between individual influence. So down here It only has to do with within-person development. Now this is all done in a single level wide format. That is, even though I say between and within, I'm talking about the same kind of model setup, single level wide, as for the traditional classic way of formulating the model. It's not multi-level, it's single level, and we have just borrowed ideas from multi-level factor analysis to formulate it this way. And now, by that thinking, then we should have invariant loadings across time and invariant factor variance, perhaps also, and invariant residual variances that come in these arrows down here across time. So it's still a single level wide model. I'm just repeating this. 2 random intercepts representing between level variation, stable over time, instead of having many correlated residuals in an undisciplined fashion. And SES is a between level variable and influences only the random intercepts. That is, we don't have any influence from SES to the F1, F2, F3. This is a key issue. This does not influence F1, F2, or F3 directly. It goes this way. In fact, you could not identify an influence from SES to all 3 of them. Clear separation of within and between. And the relationship between the factors over time, over here, represent within-person dynamics. So here we get back to this table, the classic and the new model. The new model has 6 fewer parameters, and still chi-square is, and therefore higher degrees of freedom, and still chi-square is better than the classic model. With this non-zero p-value, good RMSEA, and a perfect CFI. That's interesting. The findings for the new random intercept model, I already said this, the level 2 between level findings, talking about it in multi-level terms, although we do a single level analysis, SES has a significant negative effect on the random intercept as expected. As SES goes up, feelings of anomia and powerlessness tend to go down. And this means that SES explains part of the measurement non-invariance across people. So you have measurement non-invariance because of these random intercept, but you can model it and you can even explain it. And we're going to see how well it explains it when we take a look at the M+ outputs. And on level 1, on the within level, you actually have a positive significant effect of F1 on F2, that is from 66 to 67, but no significant effect actually of F2 on F3 from 67 to 71. So this is a much better modeling framework to work with, I think, and it should be used more often in practice than it is today, if it's used at all in this fashion. On slide 23, we've come to the last bullet of the talk. We're going to go through the M+ scripts for the both the classic and the new model for the Wheaton et al. Data. First, the classic model. We're going to remind ourselves of the fact that we're going to try a metric invariance model here, equality of loadings across time, and we're going to allow for correlated residuals for each item for adjacent time points. So A1 with A2, A2 with A3, and same thing for the P, the powerless indicator. So let's go to the M+ output. And I'm showing it in the HTML output version. It's easy to skip around in. So we have the data is a table using table 2 from the 1977 chapter for 3 time points. So we give the correlations, means, and standard deviations from which M+ computes the sample means and computes the sample covariance matrix and includes the means. 932 observations. And the model is quite straightforward. We measure the SES factor by 2 indicators, and then we measure the 3 time-specific factors of alienation by their 2 indicators, anomia and powerlessness. And we're going to deviate from the default of fixing the first loading to 1, so I have an asterisk here for the first indicator for each factor. So I have 2 free factor loadings, and I label those parameters parameter 1 and parameter 2, and they're held equal across time by this setup. And I'll choose to set the metric by fixing this variance to 1. It's actually the residual variance, but by fixing the first time point variance, you have handled the metric for all 3 time points by the fact that you have equality of loadings. So the model is identified that way. We regress F1 on SES, F2 on F1 and SES, and F3 on F2 on SES. So a lag 1 type of model. And then we allow for the residual correlations, 66 with 67, 67 with 71. First for anomia and then for powerlessness. And we're asking for Tech 1 mod indices and standardized. So we go to model fit information and we see 31 parameters and this likelihood that we had in the summary table of fit. With a chi-square that is a little bit too high and RMSEA that's also a little bit too high. Now the model results show a significant loading for SEI as measuring SES, and the loadings for F1, F2 and F3 are held equal across time as we see, and they are both significantly different from 0. And then you have F1 regressed on SES, which is negative significant as expected. As SES increases, the F factor, alienation, goes down. F2 and F1 is positive and significant, and F2 on SES is negative significant. Same for F3 on F2 and F3 on SES. And then we have the residual correlations here, or covariances rather. Pairwise, these are significant for anomia. For powerlessness, the first residual covariance is not significant, but the second one is. We don't bother with the intercepts here. We're not trying a growth model. We just ignore them. And you get the variance of the SES factor. We'll just check that it's not 0 or negative. And all of these residual variances are also positive and healthy. And then you have the factors here, F1, F2, and F3, their residual variances, where the first one was fixed to set the metric. Now you can look at the standardized solution as well and get all of the results in standardized metric. And for instance, then you can see what the correlations between the residuals are. 0.3, 0.2, 0.1, 0.1. So higher residual correlation for anomia than for powerlessness. And we have another kind of standardization, and then finally we get to, I can go this way faster, modification indices. So here we have a couple of interesting ones. Let's take a look at these first. For instance, here F3 on F1 has a fairly high modification index, the expected drop in chi-square if you free that. And that is then a lag 2 model. So F3 is not only influenced by F2 but by F1 as well. So that could help improve the model. And then if you look further down here, we have 54, a very high value. That's for anomia 71 with anomia 66. So that's a residual correlation between time point 1 and time point 3, which we didn't include. And I don't see that that is not very high for anomia, however. Oh, sorry, for powerlessness, it's not as high. So we could make these adjustments one at a time and see if it's needed or not. But we're not going to bother with that. Also, we can take a look at the R-square. R-square for anomia and powerlessness. Now, even though the loadings are equal across time, the reliabilities will not be, because the variances change over time. The total variance change over time too. So R-square is the same thing here as reliability. So the reliability of anomia and powerlessness are in the 0.7 range, and it goes down a little bit over time. All right, so that's the classic model. And then we turn to output number 2, which is for the new model on slide 25. We show it again, and just to remind you, it is a standard SEM model in the sense that it's single level. I've just drawn it in a way to emphasize that we have a between part that shows variation across individuals, and a within part that shows variation across time. So let's see how we set that up in M+. Let's look at the input instructions. So I put a couple of comments in here. I distinguish between the so-called between level and the so-called within level. Again, this is not a two-level analysis, it's a regular SEM. So on the between, that is in the left part of the picture, we have the SES factor measured by education and SEI as before. And then we define 2 random intercept factors. And they are anomia and power. Anomia measured by these 3 anomia items at the different time points with fixed loadings 1. These are the unit coefficients that I talked about earlier for random effects influencing the observed outcome. And same thing for power. That's the random intercept for the powerless indicator. And then I regress those 2 factors, those 2 random intercept on SCS as defined up here. And then I turn to the right part of the picture, the so-called within level, where I have the same loading metric invariance as before, setting the metric the same way and having the same regressions. And to make sure that I don't correlate between factors with the within factors, I have this statement. So SES-power is the SCS, anomia, and power factors, and that all 3 of them are uncorrelated with the time-specific factors F1 to F3. So no correlation across between and within, so to speak. And then I have the invariant residual variances here. The 2 residual variances for each time point are equal across time. I could also somehow try to hold the factor variances equal across time. I don't do that here. I don't think it's entirely necessary, and we are going to skip that. So let's take a look at that model fit information then. We find the 25 parameters that we talked about in the summary. That is 6 parameters less than the classic model with a good chi-square and a good RMSEA. And the model results, we have the intercept factors defined here. We see the characteristic ones. And then we have the 3 time-specific factors, which are, again, the factor loadings are significant, both of them. And the random intercepts regressed on the SCS, negative, significant in both cases and of the same magnitude. So that's saying that as SCS increases, your anomia and powerlessness random intercepts go down. F2 and F1 significant, positive, but here something new. F3 on F2 negative but not significant. So insignificant which it wasn't. It was positive significant in the classic analysis. And the rest is of less interest. And then you can also take a look at the standardized model results and the R-squares, and you can compare those values across the classic and new and think about the differences in interpretations. I'm going to turn to model modification indices, and here's all we have. 1, namely, and only 14 as compared to earlier. I think we had something in the 50s. And this is between anomia in 71 and powerlessness in 66. So the last and the first time point and different indicators doesn't make much sense, perhaps. So we ignore that, quite simply. Let's ignore that. All right, so that shows the new way of analyzing the Wheaton et al. Data. So at the end of this web talk here on slide 26, I'm going to circle back to Madison, Wisconsin, where we started the story of Webtalk 3. And it's an interesting article by Howard Weiner in the Journal of Educational and Behavioral Statistics in 2011 that has an interview with Carl Jørskog, and where he discusses the origins of Lisrel. He was actually inspired by an article by Arthur Goldberger, one of my hosts in Madison. Goldberger had a psychometric article in 1971 discussing the relationship between econometrics and psychometrics, and suggested that Carl take a closer look at it. So his Lisrel model was presented for the first time at this conference in Madison, Wisconsin in November 1970, resulting in this edited book by Otis Dudley Duncan and Art Goldberger. And Art has an interesting article there on structural equations, and I think David Wiley also has a chapter in that book. Now in 1971, after 7 years as a research statistician at ETS, Educational Testing Service, and a visiting professor at Princeton University, Jørskog returned to Sweden to become professor of statistics at Uppsala University until he retired in 2000. And after my visit to Madison, Wisconsin, 74-75, I got my PhD in 1977 in statistics at Uppsala University, where the first paper in my dissertation was this jazz article inspired by the note that Otis Dudley Duncan had left on Art Goldberger's desk in the Social Science Building. In 1982, I moved from Sweden to become a professor at UCLA, and I retired early in 2006 to focus full-time on M+. In 1976, Blair Wheaton received his PhD in sociology at this University of Wisconsin-Madison. And Blair Wheaton is now Distinguished Professor of Sociology at the University of Toronto. And with that, I end Webtalk 3. Thank you.